Hello, and welcome to Material Connection's quarterly materials review. My name's Dr. Andrew Dent. I'm VP in charge of material research here at Material Connection. I'm joined by my two colleagues, Dr. Gayatri Keskar, who is our materials manager, and also Jennifer Coppola, who is our materials researcher. Why don't you introduce yourselves, say who you are.
Sure. So I'm the new materials manager, and what excites me the most is to see what's possible with these new advanced materials. As we'll see here today, the cross-pollinating material usage ideas from one industry to other industry is definitely turning out to be one of the key driving forces for innovation.
My name is Jennifer Coppola, so I am the materials researcher here, and that's exactly what I do. I research innovative materials across different industries and across the globe. So we're really excited today to show you some areas of interest within the new manufacturing realm.
Okay, as Jennifer said, we're going to be talking about materials related to new manufacturing. Before I explain exactly what we mean by that, I thought I'd at least let you know that it is possible to ask questions. We'll be taking those questions at the end of the presentation, and you can leave them at the chat box below, either in livestream.com or Facebook Live as well. Also, if you're following us on Twitter, you can use the handle MaterialCX and the hashtag MCXReview. Okay, so let's get started. Oh, quick thing as well. In terms of troubleshooting, if the frames start freezing, just try and refresh the page and see if that works. So let's get started with the materials themselves. So we're talking about the area of new manufacturing. To us, that is sort of a step beyond just new materials. Of course, we're always interested in new materials, but how do those materials then get formed or shaped into a potential product? I actually brought along an example of basically a product as a way of showing what we're interested in. So new manufacturing to us is a way in which we can take an existing material or a new material and transform it in some way. If one thinks about a product, such as this axe, we've organized the presentation into three main categories and two additional ones. The three main categories are structure, surface, and then forming and bonding. If one thinks about the axe and thinks about structure, one thinks about basically the structure of the wood handle. Then also the structure of this, what looks like a brass head. So that is what we mean by structure, what the actual material is that becomes part of the product. The second is surface. Surface, of course, is how smooth or whether this surface has been painted. That to us is an interesting category because it's very much how us as consumers, we interact with the product on a tactile and visual level. So, you know, whether this has been plated or coated, whether this material has been planed or sanded to form a smooth surface. And the third area is forming and bonding. What that means is how basically the handle was attached to the head. How do we put these materials together? So in any one product, you're unlikely to have just one material. It's likely to be a combination. So that combination needs to be put together in some way. So we have a category called forming and bonding. So those are our three categories: structure, surface, and then forming and bonding. We have two other small categories at the end, one of which is we're interested in new manufacturing methods for natural materials, and we'll have a small category there. And then the last one is 3D printing. We couldn't actually have a presentation on new manufacturing without including that area as well. So let's get started with the materials. What we're going to do is I'm going to pick up a material. We have samples here, and then we're going to talk about the material. One of us is going to explain the material, then we'll sort of dialogue about what's interesting to us, and then sort of go from there. Okay, so the first area is structure, and my first material is actually one that I'll present. It's this material. Now, this is called Aerozero. It's actually the equivalent material to an aerogel. For those of you who know a little bit about materials, aerogel has been that sort of almost mythical material that's known as solid smoke that is ultra lightweight but also very insulative. This is a plastic version of that. The advantage of making it out of plastic, in this case it's a polyimide, is that I can make it a lot more flexible. It uses the same process, the sol gel process. It has similar insulative properties. It works down in cryogenic temperatures. But now, because it's a plastic, I have the ability then to make it into thin, flexible sheets like this, or large blocks. So that's in the main. So the manufacturing process is the same, but then the different material enables me to create something which has a lot of the properties of an aerogel, that great insulative property, but then also becomes a lot more durable. Okay, that's our first one. Our next one is actually it's a manufacturing process of textile. I'm going to have Jennifer explain.
Okay, so here we have a triaxial weave textile. So what's unique about the triaxial weave is that you've got 3 points. Typically with a woven material, you've got your warp, and you've got your weft. So this construction is a little bit different. So you've got the weft thread here, and then it's also intertwined with an X. So that allows it to have absolutely no weak points. So this is made out of silk. Typical triaxial weaves are used in aerospace. So it's taking it from one industry, aerospace, that is super high performance, and into another industry where this is typically used for kimonos.
So the triaxial weave, so I've noticed you've got a bunch of different colors there. Is that part of the process as well, the ability to change those colors?
Exactly. So it can be in many different color combinations, which essentially is going to change the pattern, because you can see the pattern here. You've got these hexagonal shapes within. This is an open version, and then we also have a closed version here, which is essentially the same exact construction, but you've got an open and closed. So you have different design possibilities with the patterning as well as the color.
May I see?
Yes.
Okay. Okay, so what you're saying is, I'm not sure whether you can see this here, so the slight variations in color are a result of are not a print, they're actually just different colored yarns, but in those angles. So that creates a very, unlike a normal, I guess, warp and weft fabric, you've got really quite fascinating changes in color in this one.
Exactly.
Okay.
Thank you.
And what other customizations are available in this case?
Customizations? Typically the color is pretty much it. You can either have the open or closed version, and then you can create different patterns based on the colors that you use in the threads.
Okay. Our next one is actually called Recrete. And I'm going to have, who's presenting this one?
This is me.
Okay,
Yes.
Jennifer, Recrete.
So this
Thank
is
you.
a very unique material. This is a cement panel, and if you notice throughout, you've got these different colors here, and this is due to different materials that have been added to the panel. So the things that have been added are newspaper, dryer lint, wires, CDs, basically a bunch of junk. So what they've done is added that to these panels. So it's not technically for structural applications as you would normally use concrete or cement panels. This is more so for decorative use and maybe more so art installation. So you're not going to have the same durability within this panel
Sure,
as you would
okay.
with typical cement panels, but it does add that element of surprise where you have these exposed pieces with the wires, the newspaper, and it's going to be a lot more, it's going to be lightweight compared to conventional.
Okay, so I'm manufacturing this panel, so they're basically collecting junk from around. I mean, it sounds like it's basically junk from household stuff
Exactly.
or construction.
Exactly. Yep.
Okay.
And they're adding that to it. So you would think that it may be a flammable issue, but because of all of the materials that are being mixed within the cement, it makes it incombustible.
Okay, so the cement itself is basically infiltrating all those materials like paper. Typically, it would burn quite easily, but because the cement is adding into the paper, it's sort of mixing with it and then before making it incombustible.
Exactly.
Huh. Okay. Thank you. Okay. The next one is actually for me is very fascinating. This one's actually I'm not sure whether you can see what this is. It's actually a coffee pod. Why it's interesting to me and why it's as part of our new manufacturing is because it's a biopolymer, and biopolymers historically have had problems with their temperature resistance. This, through a new manufacturing process, it's a relatively basic biopolymer. It's actually a PLA. For those of you who know materials, PLA is probably one of the most well-known bioplastics out there, a lot of commercial use for it. It has challenges though because its temperature resistance is relatively limited. However, this one, by simply changing the manufacturing process of the material, they basically take two different versions of the same PLA, chemically they just mirror versions of each other, combine them as part of the manufacturing process, and just that intimate mixing creates a plastic which can withstand up to 230 degrees centigrade. So it has no problem being put in a coffee maker, an espresso maker, so it can withstand those sorts of temperatures. So to me, it's not a new material, it's an existing biopolymer, but it's that change in manufacturing process where the combination of the two different types of biopolymer are intimately mixed and then manufacture this product. So to me, that is a new area that biopolymers can reach, which is the high temperature resistant applications. Okay. Our last one is actually it's a fabric, and I'm going to have Jennifer again explain this one.
Yes. So this is a 3D knitting process. So you can see it has a unique egg crate-like structure. It's got a nice tactile effect. So this is all thanks to the 3D knitting machine. So typically you've got a 2D textile. It's flat. You can wrap it around curved surfaces, but this is adding that unique height, that unique textural effect. So typically these knitted materials are used for apparel. So here we're seeing it used in upholstery. So taking a material typically used for apparel, taking it for using it in home furnishings, or so for lampshades.
So, okay, so can I change the structure? So what can I do in terms of customization? Like I've got these sort of little egg crate effects. Can I do different effects?
Yep, you can create different shapes, and also you can have different colors.
Okay, so I mean, I don't know whether the audience at home knows, but the new sort of type of sneaker manufacturer is using a knitting process. Is it the same sort of idea?
Yes, exactly. It's the same sort of machine. There are different types of 3D knitting machines for different applications, and this is specifically, for this construction, so it can be used in a wide array of applications.
So it seems to be taking a material which is typically a two-dimensional flat surface, as most textiles are, and it's creating 3 dimensions out of it. It's creating volume.
Exactly. It's creating that unique surface effect, and as you can see here, very interesting. It has a nice height to it, nice texture as well. If you feel it.
It's interesting because I almost want to feel as though these would flatten out easily, but they're not. They're actually built into the structure. That's what to me is interesting.
Exactly.
Okay. Thank you. Okay. So that was our first section called structure. We're now going to move on to our second section, which is to do with surface. If you remember our axe, it's to do with what that surface looks and feels like. So we've moved on from the body of the product through to more sort of decorative and functional aspects of the surface of the product. We're going to go through a number of different materials in this one, and my first one is actually a molding, it's part of a molding process. This one for me is exciting because it is a way of changing injection molded parts to give different textures and effects on the outside surface of that part. Why is that interesting? It's because it gives the possibility of not having to paint or plate that plastic. Typically, if you look in many products made out of plastics, people want to improve the quality of the surface by plating or painting or when you actually make the products, you want to try and sort of make it look higher quality, and people often do that as a way of sort of enhancing the value. Here, the product is really just using the base plastic itself. So the process is quite simple. Your regular injection molded part, which is this piece, what you do is you add an additional bit of machinery on the outside. And as the part is being molded, what this process does is it heats up using induction a very top surface of this molded part. Induction heating is the same as induction cooking. It's basically a process where you can heat just small sections of that part. So it comes, as it's being molded, the top surface then gets heated up such that it actually melts. And in melting, as it solidifies, it becomes glossy and a very, very high quality surface. So I can get high gloss, as in this area as well, but I can also get texture as well. So it allows me to create very high quality, high gloss surfaces in regular injection molded parts that increases their value. Where do we see this? Large format TVs around the outside of a TV, that's a good example of one. Also in things like coffee makers on the sides. So it enables me to have much greater control over the surface quality of my product. One of the biggest problems we also found with injection molded products is that they have what's known as parting lines or mold lines, where if you ever look at a shampoo bottle, around the shoulder of the shampoo bottle, often you'll see color variations. That's because when it's molded, the color doesn't go all the way through. This will be able to solve that by simply melting that top surface and then sort of smoothing out or evening out that color effect. Okay. Our next one is Ventiflock.
Yes.
Jennifer talked to us about this one.
Yes, this is Ventiflock by Fritza. So this is a flocked material. What you'll notice here is it has this pattern that is scattered throughout. So typically with flocking materials, you've got this surface and it's flat. It has that fuzzy-like texture, but it doesn't have this high of a pile. The pile is essentially the height of the fiber that you'll notice on this fabric here. So it creates a much more fuzzier feel, a fuzzier texture, creating that high pile. So that's achieved by the adhesive is essentially printed onto the surface within this pattern, and the fibers are scattered so that they fall onto that adhesive. Then it's electrostatically charged so that the fibers stand up on end. The same way that your hair would kind of be staticky, right? It's going to stand up on end.
Sure.
Yep, it's got that same kind of effect. So this is typically used in apparel. It can be used in home furnishings, wall coverings, and you can change the color, the base color, which is the fabric, and then you can also change the fiber color. So you can create different patterns. Here we've kind of got a zebra-like pattern, but it really can be customized depending on what you want.
Merci.
Yes.
Okay, so basically the height of these fibers, I don't know, yeah, I've never seen it quite this high. So it does change very much what the idea of flocking is, because I always think about flocking. I think of perhaps packaging and lower quality products. It's a very understood and known surface. So this kind of changes it up quite a bit, doesn't it? It creates a very tactile effect. Okay. Okay, still within surface, we've actually got some metal coatings, which I'm actually going to have Gayatri explain. So there you go. Z-Rock, isn't it?
Yes.
Okay.
So these are the durable hard coatings which are made from a metal ceramic, and they can be applied to pretty much any kind of substrate. So they can be applied to metal, plastic, wood, glass, or even, as you can see in this case, textiles. And what it does, it actually improves the abrasion resistance as well as it provides a metallic luster. So it can be used for both the mechanical as well as decorative applications. So it beautifully combines the form with the functionality, as opposed to other surface coating treatments which typically tend to wear off pretty easily, and they don't offer that much variety in terms of colors that can be obtained with them. This one, it uses a zirconium-based metal ceramic, and it uses low temperature vacuum coating technology. So that's why you are able to coat on any kind of substrate, and by just varying the composition during the coating as well as the thickness of the coating, you can get a really wide range of colors. So it can be anywhere from light yellow to black. And it's also possible to get different gradations depending upon at what time you introduce different gases during the coating. So it uses carbon, nitrogen, and oxygen gas during the coating. And so depending upon at what time and for how long you introduce those gases, you can have like really wide range of colors.
Okay, so you got a blue one there. So
Yes.
so just by changing the gas in the chamber, I can change the color of the surface.
Exactly, because you are ultimately changing the composition of the metal ceramic. So it can go from like zirconium nitride to oxide to carbide.
Okay, so what's my range of colors? What can I do? I've
So-
got blue there, but what else?
You can do pretty much any color you want. So you can go from like light yellow to pink to purple all the way to black.
And these are all super hard, durable coatings.
Exactly.
Huh. Okay. Where's it being used right now?
So it's been used in a wide range of applications, anywhere from high-end kitchen or bathroom fixtures to
sure.
industrial tooling to plastic molds. Also, the other thing about what is interesting about this process is it's a dry process, so it doesn't involve any kind of harsh chemicals which typically would be used.
Such as chrome plating, that
Exactly.
sort of thing. Okay. Yeah.
And so that's why it is like a nice, safe alternative to chrome plating, and it doesn't involve any kind of off-gassing or any VOCs.
Okay. Sizes. How big can I plate? What sort of size can I put down?
So it's a little limited in that way because you have to do it under vacuum. So depending upon how big your vacuum chamber is, that will limit the size of the substrate you can use it for.
I see. Okay. And talk to me, you mentioned the textile, okay.
Yes.
So it's coating the surface. I can see here it looks metallic. So is it coating every single fiber or just as a top layer?
It's coating the top layer.
I see,
But again,
okay.
you can vary the thickness of the coating if you want to have a little like thicker or harder in order to cover each and every strand of it.
Okay, so basically what I've got is a super hard zirconium-based coating on a textile here.
All right.
Fascinating. Okay, thank you. My next one within surface is actually a glass coating process. This is interesting to us for many reasons. This is a process which uses a ceramic-loaded ink and deposits it on glass, and then in a way fires it or bakes it so that that ceramic is sort of baked into the glass itself. What's interesting to us about it is two things. First of all is its resolution. This image here, you can see, I think it's a leopard there, but you can also see a gradation of color there. This is actually at 720 dpi, so basically beyond my eyesight's resolution. So you get very, very high quality, high resolution images. And what's also interesting is, you'll notice, you can see the image of the leopard there. If I turn it around, exactly the same. So the quality of the image is such that I can get high resolution images, which is just played on one side, but actually can be seen on both sides. So this allows me to have vision on the surface both ways, which is rare in this sort of coating process. Sizes, very large, up to 4 meters by 3 meters in terms of size. So very large format pieces of glass. Can only go on flat. That's one of the challenges, so it has to be a flat plate. But because it's been put down as a ceramic layer, ceramic ink, it's very durable. Durable to ultraviolet light, sunlight, weathering, scratch resistance. Applications, one can imagine things like home appliances, large format home products. But really for us, it's the high resolution effect. It's how to create on glass a very, very high quality image using a ceramic which is as durable as the glass itself.
So can it also be used for outdoor applications?
Yes, there's no reason why not, because the ceramic, I guess, would withstand rain, high temperature, low temperature, ultraviolet light. So yes, there's no reason why you couldn't put this on the outside of a building, I guess.
Exactly.
Okay, yeah, exactly. So that's a good application.
So you said that it is durable, it is scratch resistant. Can you see it, please?
Yeah. So because it's a ceramic, so the way they put it down, they put it using the same sort of idea as I guess a digital or inkjet printer. So they're putting down the ink, but the ink contains lots of ceramic particles, very fine ceramic particles, and those ceramic particles are coloured. So that the ink goes down, what they do is they then bake the whole surface. The liquid that was used to put the ink down evaporates off. So that comes off, and then you're just left with a ceramic which sticks on hard onto that surface.
Awesome, thank you.
Sure. Okay. Okay. So our next section is bonding and forming. Remember, again, let's go back to my axe. Bonding and forming is how we're basically putting together the handle and the head. It's areas such as gluing and different ways in which we can then form and shape in order to make sure that you put your product together as a single piece. My first one is something called fluid cell hydroforming. Okay, so I'm going to show you a couple of examples here. This one is quite a basic one. It's obviously just a formed metal sheet. This second one is really quite more the fascinating aspect. Fluid cell hydroforming is a process used in automotive and also in industrial, and it uses water, the incompressibility of water. Water, no matter how much you press it, does not compress. Unlike a material such as rubber, which can compress in, water does not compress. So it's very effective at transferring pressure from one point to another. So what they do is they take basically a sheet of material, which starts off as flat in this example. They will then put it into a die. So I've got an example of a die here, and I take my flat sheet, and then what I use is I use a bladder, very much like a water-filled balloon, and press that down using very high pressure. And what it does, the balloon itself forces itself into all of the holes. So in this, it would fall into these holes here. Here, it would obviously force itself into the letters themselves. And the bladder is very effective at pushing that metal into the various different shapes. So that's a simple process, but it's very effective at making sure that any part that's been produced this way has a very uniform wall thickness. So if I can press, let's say I push something like a beer can, so I can push that material all the way through and make sure that the wall thickness was the same all the way around. This is very good for industrial applications because it ensures that you've got consistent strength. Another interesting thing about this, is because the form onto which it's pressed, in this case this piece, you can 3D print it. So I can very quickly, using this process, 3D print a shape, take my metal piece, press it down. So I'm able to create forms very quickly just using a 3D printing, and this is actually a good example of how it's used in different industries, often not seen by the consumer, where we've actually got a process where I can very quickly create intricate shapes on my metal simply by printing the form I need to press it into and then using that as part of the process.
Interesting.
Very interesting.
Oh, quick thing. Types of metals. Any metal you like, any metal that I can press. So obviously this version is aluminum. We can use steel. But we can also, you could use copper and gold and zinc, any material really that would form in that way. There are very few materials that don't do that. Some are, I think zinc is not a particularly good one, but the rest of materials are pretty good at forming and shaping in that way. So it's really quite versatile in terms of materials. Okay. Our next one is still part of our bonding and forming, and is actually quite a sharp material. I'm going to have Gayatri explain this one.
So compared to all high-tech materials we have seen so far, this is something which is really simple but effective solution in order to bond to similar or dissimilar materials. So what we have here is actually a thin gauge metal sheet which has, as you can see, a series of hooks or spikes on either one end or both sides, depending upon whether you're using it for the laminates or to bond different materials. And this hook formation actually allows it to form adhesive-free mechanical bond. So it doesn't involve any kind of chemical additives that are used in order to join these two materials.
Okay.
And then other great thing about this one is also improves the mechanical properties by 2 to 3 times just by using the metal film in order to combine these materials. So the advantages are because you're not using any chemical additives, it obviously cut down your production time, energy and cost, because now you don't have to worry about having extra additional steps in order to prepare the surface or curing steps that otherwise would be necessary if you are using chemical additives. And also it eliminates any kind of off-gassing or VOCs.
Okay.
One of the challenges we have seen in case of composites is the recycling of dissimilar materials.
Sure. Yep.
So it is relatively easy to bond any two surfaces, but it also works to pull them apart, as you can see here, pretty easily.
Okay.
So that way it facilitates the recycling of dissimilar materials.
So these pieces, I can make them large? There's no limit to the size of these pieces?
Yes, you can make them large. So you can actually use them to join, say, like metal and wood, or even plastic, as you can see in this case, or you can also cast concrete around it. So it can also be used for concrete reinforcement. So it can be used with like really different kind of materials in that sense.
So it's basically a simple way of sticking materials together and giving them additional strength.
Exactly.
Okay, so I was thinking about, okay, what if I've got a large format piece of metal that typically I have to glue onto a tabletop?
Right.
Maybe it's a laminate or something like that. In this process, I can simply just press it down, no need for glue, and at the end of its life, I can simply just remove this metal, put it in the recycling bin, and then remove the plastic.
Right.
It's a simple idea, but
Right.
it seems like, I think that's what I love about this sort of thing. So how do they actually, do you know how they actually manufacture, how they create these spikes themselves?
Actually, I'm not very sure about that.
I mean, what it looks like they're actually gouging. You probably can't see this on camera. It looks like they're actually gouging the surface. So it's basically just almost gouging the metal and lifting up a little spike. It seems to, if you look at there. Okay, so it seems a relatively simple process, but really just very effective results.
Definitely. And so it can be used for wide applications, anywhere from like construction for flooring, composite laminates, or concrete reinforcement in automotives, aerospace. So it can be used for pretty much any industrial applications where you will need to combine or bond two materials without losing any mechanical strength.
How do I press them together? Do I have to use a hammer? Do I need a lot of force? Can I do it by hand?
So actually, they can be pressed together either using high pressure, or you can actually preheat the material, as in case of thermoplastic, to soften it to make it easier.
Okay. Yeah.
Or in case of concrete, just pour it around it. So that way it will be incorporated into the structure itself.
Okay. Thank you. Okay. Our next one is actually it's the combination of two manufacturing processes that enable a simplification of a basic need. Okay, so this started off in automotive. Automotive has two main challenges. Of its many challenges, there are two main ones. One is lightweighting. In order to make the cars more efficient, make them faster, make them more fuel efficient, they need to reduce the weight of the car. The second area is actually there are really quite stringent requirements for automotive in order to reduce the environmental impact of their cars. They need to be more recyclable and to use more natural materials. So this process is a combination of lightweighting through removal of things such as bolts or welds or other affixing materials, and also the use of natural fibers. So the natural fiber sheet, which is this top surface, structural, it's quite stiff. It is created simply by pressing together some sort of moist fibers in a process that presses and forms them together. It rigidizes, it creates this nice structural form. At the same time, you've got an injection molding process that is basically putting together this part. If they're done at the same time, they're both warm, and what happens is the plastic itself just is warm enough to then stick itself to the natural fiber. What's good about this? The good thing is it reduces the need for glues, it reduces the need for bolts, and it enables a combination of materials, one of which is relatively simple, which is the natural fiber. In this case, I think it's a flax fiber, and a much more complex piece. Where we might find other applications for this, let's you decided you wanted the outside case of your laptop to be made out of a natural fiber. So my top surface is my natural fiber. I can then mold in my complex, intricate parts out of plastic, which then allow me to house the battery and the wiring and other screws and that sort of thing here. So I don't have to worry that my natural fiber isn't able to deal with that degree of complexity. It's a combination of the two processes: injection molding, fiber pressing, but both together at the same time, and sticking them together to give that intimate bond.
So are you limited to what type of material you're using for the composite?
A little bit, but you could use most plastics for this part. This case, I think it's actually a polypropylene, but you can use ABS, typically used in automotive. The fiber composite, most actual natural fibers, kenaf, jute, flax, those sorts of things. There's no any reason why you couldn't use perhaps waste material, let's say denim fibers or old waste cotton fibers, that sort of thing.
Right.
Nice.
Thank you.
And our final one within the bonding and forming is actually a material that looks really quite simple, but to me is really quite revolutionary. It's a foam. It's basically just a regular type of foam. And it is supposed to be an alternative and a replacement for regular other lightweight polymer foams, expanded polystyrene, polypropylene, those types of materials. But what this is made out of, though, is foamed out of the waste material from paper making. When you make paper, you use a lot of water, and you basically take the cellulose fibers, the long fibers, and make the paper. What happens as you wash that paper is that you get a lot of tiny fibers that get washed out. They're not big enough to be useful to the paper. They just go through the sieve. So they're waste. So you end up with this a large amount of waste sludge at the end of that process. Not really used for much. It's typically a waste material that has zero value. This company has been able to take that sludge and then transform it into what's known as NanoCrystalline Cellulose. It's a complicated name for what is basically just very, very tiny forms of cellulose, little, almost, nanostructured, smaller than the eye can see. In doing that and actually separating them out and aligning them, you can actually end up with a material that can have really quite good structural strength. It's the reason why they say sequoias can stand so tall. It's because of this really quite intricate structure of these cellulose materials. So what can I make out of this sludge? In this case, it's a foam. The material can be foamed. It has good strength. It's quite versatile. One can, of course, color it as other foams. And the good thing also is that it comes from a renewable source and can also eventually, I think, be composted. So it offers an alternative to our existing foams that has a much more renewable story.
So are there any kind of limitations?
At the moment, it's a relatively new manufacturing process, so it's not a large scale, so we're not getting large companies doing this. It's still, although commercially available, it's still on a small scale. So costs are a little higher than our current regular polystyrene foams, mainly because of the efficiencies of volume. But the raw material is waste. It costs them virtually nothing to actually take that material and use it. So it has the potential to come down in price quite a bit.
Do you see people using it on a larger scale in the near future?
I hope so, because I think part of what we love about Material Connection and what's important to us is trying to find new ways of using readily available materials. So anything comes from waste, anything that is renewable. We love when people use those. I think what we're going to need to find is that killer application where someone says, this material works better than any other, and I can't use my regular polymer foam, I need to use this. And then once it gets that application, you get enough volume, and then people start recognizing it and then using it for other uses.
Makes sense.
Okay, so those were our three sort of main categories. We talked about structure, we talked about surface, we talked about bonding and forming. We wanted 2 other categories to sort of, because we felt as though these didn't quite fit into those main ones, but we thought they were still interesting and of value and wanted to share them with you. Our next one is where we're actually finding natural materials are being processed or manufactured in a new way to give either different performance, improved performance, but sometimes also low environmental impact. So the group we have now is sort of in the naturals arena, not necessarily sort of groundbreaking in terms of super high performance, but just using our existing natural materials and providing them with a sort of a potential for a different or new application. So, which one do we want to start with? Okay, we're going to start with the timber. So, Gayatri.
So performance requirements most of the times limits the kind of wood species you can use for the outdoor applications. And even though some materials or wood species that can be used outdoor, they are typically chemically treated in order to make them weather resistant. So Arbor Wood Company has come up with a way, which they call it as a thermal modification process, in order to alter the cell structure of the timber just by using heat and steam, in order to improve the performance. So virtually you can use any other or maybe inferior indoor wood species for the outdoor applications.
Okay.
So the way it works is it is a 3-step heat treatment process. So in the first step, it is heated to around 100 degrees C. And what it does, it removes any kind of moisture from the wood in order to make it more dimensionally stable. It also reduces the swelling or shrinking of the wood by roughly 60% as compared to unmodified wood.
That's huge.
Yes.
Okay.
So the second stage is a high temperature step where it has been heated to 200 degrees C, and that one is more used in order to form more even tone color throughout the wood species. So in place of using chemical stains in order to get different color variations, in this case by just changing the cooking temperature and time, you can get wide range of colors within the single species.
So the color is running all the way, that color is running all the way through the thickness of the material?
Exactly.
Huh, okay.
And then the third and the last step is where it's been cooled down using water in order to re-enter precise amount of moisture into the wood. So another interesting thing about this wood is because it doesn't use any harsh chemicals, so that way it is more environmentally safe and natural way in order to get appealing exterior appearance as well as making it weather resistant for the outdoor applications.
Okay, so you mentioned lots of different types of woods. Do you know what that version is, what that material is?
So this is actually the ash wood, if I'm not wrong.
Okay, fair enough. So and if I've got ash, I can then change the color of my ash plank from what it was originally, like the natural wood, and I can basically go through a full, like a range of different color effects.
Exactly.
So it can be used as a way of almost, yes, creating decorative effects within the wood as well as its performance improvements.
Right. Exactly.
Okay. Any idea about length of time I can use it outdoors?
So actually it will eventually wear out, but you can use UV inhibitors in order to prolong its lifetime.
Okay. Okay. Thank you very much. So thanks very much for watching. We appreciate your attendance. Okay. Sorry, my apologies. Sorry, we have one more section to go. We have what we couldn't miss out on is actually 3D printing. No area of new manufacturing can be complete without the area of 3D printing, but we wanted to include some materials which were specifically sort of new ways in which the 3D printing area of manufacturing has shown innovation. So we've got a few examples here. We want to show them to you, and actually we've got a couple of demonstrations as well. So Gayatri, why don't you take us through some of the 3D printing innovations we have? Sure.
So as Andrew mentioned, 3D printing has been around for a while now. But what we are more excited about is the recent innovations in terms of materials, processes, and techniques, which has made it possible to have like high quality, high resolution 3D printer, which is much more affordable now. And also the material innovations have made it possible to actually impart new functionalities into the resin that's been used for making these 3D printed objects. So the first one here we have is photopolymer resin that actually features shape memory properties.
So this has been 3D. So this object's been 3D printed.
Yes, it has been 3D printed. So as I will show you here,
So what are you putting it into?
so this is a hot water.
Okay.
So the way this works is if you can apply high heat to it, actually you can change its shape, as I will show you in a minute.
Okay, so you're making him warm and sort of malleable.
Exactly.
Okay.
And then you can just change, it's not warm, hard enough. And then you can change its shape, and once it's cooled down and again subjected to heating, it will remember its shape before deformation and it will return to it.
Okay. So yeah, I've heard of shape memory polymers and that property. So this is basically a shape memory polymer, but in a 3D printing form.
Exactly.
Okay. So can we move him?
Yes.
Okay, now he's moving. Okay, now he's waving at us.
And then now I'm dipping it in the cold water
So why do you dip it in the cold water?
just to stabilize the shape I have changed it into.
Okay, so he stops becoming malleable. He's now rigid in that form.
Exactly.
Okay.
And so it can be used for different applications, such as like regular rapid manufacturing, prototyping, as well as multifunctional toys. And one of the proposed application is actually it can be also used for 3D printed furniture. So for example,
Okay,
you
you're
can,
gonna have to explain that one.
yes, sure. So what that means is now you can have actually furniture which you can close back together during the transportation or storage, and once it goes to its destination, then you can actually just return it back to the original shape you want it to be.
Okay, sounds fascinating. Okay.
And as you can see here,
So okay,
it
so
is-
he was waving. Now our intention is once he goes back into water, then he should revert back to his original non-waving state. Something you're
Exactly.
saying. Okay, fair enough. And how many times can I do this?
you can do it multiple times. So that
Okay.
also makes it really interesting that you can have different kind of shapes from just using one material. You can have
I
different
see, okay.
designs.
So I could have my 3D printed chair, and then also basically have it in different reclining levels.
Exactly, you can do that.
Okay, so what's our next one?
So the next one we have here is actually ceramic clay. So this is based on the porcelain formulation. So it has a similar kind of thermal tolerance as well as electrical resistance. So it can be food safe, microwave, dishwasher safe, or you can also use in the freezer.
Okay.
And so what interesting about this one is now actually 3D printing is moving away from just making like models or prototypes into making more realistic objects. So
Okay.
it's entering into our day-to-day life. So I can see it being used for making your regular china, so that way you don't have to worry about your fancy china getting broken when you're using it on a day-to-day life. And so once the object is printed, it needs to be fired at 2200 Fahrenheit in order to give its desired porosity as well as mechanical strength. Then later it can be glazed in different colors to give different variations.
So this basically looks like a regular glazed pot.
Exactly.
Okay, so if you asked me, I would have said this was simply just thrown. It wasn't 3D printed. So it's producing products that look exactly like a regular.
Right.
That's amazing. Okay.
And so it's also sort of bringing something as ancient as ceramic industry and automizing it in order to make something which will only be possible using 3D printing.
Okay. So I just want to go to our final material. This one you probably saw it during the invitation, but I want you to explain this one, which is our T-Rex head.
Yes. So what we have here is the carbon fiber reinforced PLA. So as you mentioned before, PLA is most commonly used bioplastic. And here what we have is roughly 15% by weight chopped carbon fiber that has been incorporated into a PLA.
Okay.
And what it does is, because of the carbon fiber, it gives its additional structural stability as well as strength. So that's why it's possible to make like really complex shapes which otherwise wouldn't have been possible with any other processes.
Okay. So I'm basically looking at a carbon fiber composite, but made through 3D printing.
Right.
So a lot of the same sort of strength. So the sort of the color I'm getting, that's from the carbon fibers themselves.
Right.
Do you know how big the carbon fibers are in order to print them onto that surface?
So I don't know roughly what's the dimensions of that, but these are the chopped fibers. And so if the regular 3D printer head might not work in that case, they also have some add-on accessories that can be used in order to make it work.
Wonderful. Okay. Thank you. Okay, so that basically wraps up our sort of materials review in the new areas of manufacturing. You've seen a range of different ways in which materials are influenced by the way they're manufactured, from structure through to surface, through bonding and forming. We had some natural materials and also some 3D printing. Of course, we'll be able to take some questions, which hopefully you've been sending them. If you have more questions, you can of course put them in the chat box below, Facebook Live and also livestream.com. Do we actually have any questions that were asked? So I think a colleague of mine is actually texting them through as we go. So hang on a second. Where are we? Okay, so our first question, actually, it's. Let me actually ask it of you, Gayatri. The world of additive manufacturing seems to change so quickly. Where do you see it heading next? What new materials or new techniques might happen?
So I think I might have covered few applications of materials during the presentation today. But another point I will definitely like to add is more about hybridization using 3D printing. So in that case, you are not using 3D printing just by itself as a manufacturing process, but you are combining it with the available traditional manufacturing processes in order to customize the products.
Okay, so like almost in the way that we had for this, where you're using 3D printing as an add-on, as an additional to existing manufacturing.
Right.
Okay. Okay, so we've got another one. What is an example of a new manufacturing that you may not have shown today during today's live stream, but that you're excited about? I'm going to have Jennifer answer that one.
Well, something that I'm excited about is more so biomanufacturing. So anything that really includes using mushroom for packaging, like the mushroom mycelium, or using the bio-leather that is grown from bacteria, things like that are really exciting to me.
Yeah, I mean, I have a personal love of that as well. I think, that areas where we're seeing just the enhancement of existing natural materials, through really quite creative and innovative ways. That to me is exciting too. Okay, so we've got another one, which is how does induction molding compare to InMold decoration? Now remember I showed you this one, which was our induction molding process. It differs by InMold decoration because InMold decoration requires an additional film or layer on the outside. Typically this is printed, sometimes it's just as a wear layer, sometimes it can even be a fabric, but it's always an additional film that's then applied and then this is molded onto it. This differs because this is just 100% plastic. It requires no additional film and the top surface is altered by melting it rather than putting that layer on. So there is basically a fundamental difference. And this also works on regular injection molding machines, whereas with insert molding, you typically have to have a specialized machine in order to do that. So this is basically an add-on, and it does fundamentally have a difference because of that. It simply is just 100% that material and no additional layer. Okay, do we have any others that are coming through? Okay, so I'm getting a nod from my colleagues. Okay, so we've got a next question. I'm going to let Gayatri answer this one as well. How close are 3D printed fiber parts to traditionally made carbon fiber parts?
So as we have seen in this case of T-Rex, the mechanical strength is pretty close to what you will get with the standard processing.
Okay.
So just because you are 3D printing the parts, it doesn't take away its mechanical properties. So it will be at par with whatever you will get using the same composition with the traditional techniques.
Okay. And I think this is there's a follow-up question to the same one. Is there a weakness at the printed layers junction? So as you put down each individual layer, is there a weakness there?
Actually, there is no weakness in that case, because as you can see in this case, as it was really hard to even figure out.
Yeah, I'm talking about the carbon fiber.
Oh,
yes.
okay. Sure.
So as they print the individual layers, they're asking basically because you've got a fiber layer and then you're sticking another layer on top, because you don't get bonding between or fibers between the two, are you getting a reduction in that strength?
I don't necessarily think we get any kind of reduction in the strength in the vertical direction just because you're having layer by layer assembly.
Okay. Yeah,
What are your thoughts on?
Yeah, my thoughts are that maybe as a result of the PLA being molten, as it goes down, there might well be a little bit of fiber uptake into that second layer. I think, yes, you might get a small amount of difference, but I think what you need to do is you need to print in the orientation which you are least concerned about its strength. So let's say you've got a part, and what's important is its flexural strength. Then I want to print it in a particular orientation so that the fibers are always in that direction. So I think that would be probably the simplest and best way. So you'd have to engineer in which direction you print in order to maximize its performance.
But in using a binder or something like that, will it help to actually solve this issue?
I think, well, the PLA itself would act as oh, you mean in between each
Yes.
layers? I'm not sure. I think we'd have to rely upon just the PLA, because otherwise you're going to get a mixture of plastics. Yeah. Okay. I think that was our last question. So all that's left for us to do is to thank you so much for watching. Of course, if you have further questions, you can always email us at info@materialconnection.com, and also our Twitter handle, which is materialcx. So it's goodbye from Andrew Dent, and if you want to sign up as well.
Sure. So we are glad that you were able to join us today, and we hope you really liked our selection.
And we hope that you join us next time for our next webinar. Thank you.
Thank you.